Hey guys, it's Ted, and today we're going to talk about more techniques of integration. In the last video, we talked about U-Substitution, integration by parts, and how to solve trigonometric integrals. Today we're going to talk about trigonometric substitution and partial fraction decomposition. So trigonometric substitution, or as I'm going to call it, trig sub, is different than U-Substitution. In U-Substitution, if you remember, we substituted U as a function of X. But in trig sub, what we're actually going to be doing is substituting a x as a function of theta. So that's going to play out very differently. And we're going to use three identities to help solve these integrals. First one is that cosine squared of theta equals 1 minus sine squared of theta. The second one is that secant squared of theta equals tangent squared of theta plus 1. And the third is just like this one, it's that tangent squared of theta equals secant squared of theta minus 1. And you can really easily obtain that just by subtracting 1. So there are three different forms of integrals that we can use trig sub to find, to solve. The first one is if there's something in the form square root of a squared minus x squared. Second is if there's something in the form x squared plus a squared under a radical. Finally, if we have the square root of x squared minus a squared. You'll notice I wrote each of these under one of these identities. That's because this one, you can see it kind of resembles this identity because we have a constant minus a variable squared or a function squared. Here we have a function squared plus a variable. Here we have a function squared minus a variable. So those are the three cases we're going to use. So let's look at some examples and go over how trig sub actually works. First one we're going to look at is a simple one, the integral of the square root of 9 minus x squared dx. And so you'll notice this is in the form of a squared minus x squared, so we're going to use this identity somehow. So here's what we're going to do. We're going to substitute. First, we can rewrite 9 as a squared. So this is going to be the integral of 3 squared minus x squared dx. And here's the substitution we're going to make. We're going to let x equal 3 sine of theta. And that'll make sense why we're doing that in a second. But notice this a, which is 3 in this case, is our coefficient of the sine of theta. So now we have to find dx. So dx is going to be, let me put it down here, dx is going to be 3 cosine of theta. And now notice what we can do with this. This is going to be equal to the integral of 3 squared minus 3 sine theta squared times 3 cosine theta. Oh, this should be a d theta here. When you're when you're doing a substitution, you always have to put another differential on this side. Times 3 cosine theta d theta. So we just plugged in 3 sine theta for x, and now we're going to square it. Let's see what happens. I'll move it down here now. This is going to be equal to the square root of integral of the square root of 3 squared minus 3 squared, I'm going to leave it like that, times sine squared of theta times cosine theta d theta. Now what we can do is we can factor out a 3 squared from both of these, and we get the integral of 3 squared times 1 minus sine squared of theta times cosine of theta d theta. Now you'll notice, if I close this parentheses here, 1 minus sine squared theta, based on our identity, is cosine squared of theta. So we can rewrite this as the integral of the square root of 3 squared times cosine squared of theta times cosine of theta d theta. And now, you'll notice both of these, this is one term and it's a perfect square. So we can just take the square root of that and we get the integral of 3 cosine theta times, still 3 there, and there, and there. I really forgot to write 3 times. 3 cosine of theta times 3 cosine of theta d theta. Now, moving things down here, we can multiply these two together. We can pull out a 3 and times 3. I always like to pull out the constants in front, so we get 9 integral of cosine squared of theta d theta. And you know, this is a very easily solvable integral. If you remember solving trigonometric integrals on an identity we can use to solve this, is that cosine of 2 theta equals 2 cosine squared of theta minus 1. So simplifying that, we get cosine squared of theta equals 1/2 times 1 plus 2 cosine. The 2 here went down to the 1/2. So 1 plus cosine of 2 theta. All right, now we can simplify this. So I'm going to pull out this 1/2 again. So we get 9/2 times the integral of 1 plus cosine of 2 theta d theta. And if we evaluate that integral, we get 9/2 times theta plus 1/2 sine of 2 theta plus c. All right, now we can do a little bit of cleaning up here. We get 9/2 theta plus 9/4 sine of 2 theta plus c. And that's our answer, right? Wrong, because this is in terms of theta and our original was in terms of x. So you might say, well, how am I gonna, if we know that x is 3 sine of theta, how are we gonna figure out what sine of 2 theta is? Well, here's what we're gonna do. Since x is equal to 3 sine of theta, that implies that sine of theta equals x over 3. So what we can do is draw a triangle, a right triangle. If you look at this expression right here, sine of theta equals x over 3. That means we have an angle theta, the sine of that, which is opposite over hypotenuse, is going to be x over 3. And so if we solve for this side right here, we'll get square root of 9 minus x squared. So that looks familiar. That's our integrand here. So yeah, that's because we figured out that that's actually equal to 3 cosine of theta. So if this is 3 cosine of theta, that divided by 3 is going to be cosine of theta, which is adjacent over hypotenuse. But I'm getting ahead of myself. Sine of 2 theta, if you'll remember, we have an identity. This is going to be equal to 9/2 times, and if sine of theta is equal to x over 3, that means theta is the inverse sine of x over 3. So that's how we're going to write it, 9/2 times the sine inverse of x over 3. And now sine of 2 theta can be written as 2 times the sine of theta times the cosine of theta. That's an identity we learned in pre-calc. So we're going to multiply by 2, so I'll cancel out the factor of 2 in the denominator here, so we'll end up getting 9/2 times, I can just write it here, sine theta cosine theta. Theta plus c. And now finally what we can do is write sine cosine in terms of x, because we have this triangle here. So we have 9/2 times the sine inverse of x over 3 plus 9/2. Well, let's see what we get here. The sine of theta we know is x over 3, and the cosine of theta is going to be adjacent over hypotenuse, which is 9 minus root 9 minus x squared over 3. And since we're going to be multiplying two things, they both have a 3 in the denominator, that'll mean there's a 9 in the denominator, so that'll cancel out with the 9 here. So we'll end up with the 9 here, so we'll end up getting 1/2 times x times the square root of 9 minus x squared. And that used to be 9/2 times x over 3 times square root of 9 minus x squared over 3. But I just cancel out these 3's with that 9, and we get this as our answer, plus c. So trigonometric substitution makes things easy by putting them in a form of a trigonometric function that makes it a lot easier to evaluate this integral. Let's look at another example using another one of our trig sub rules. We have the integral of, let's say, dx over x squared times the square root of x squared plus 4. We could not normally solve this using substitution because the derivative of this radicand right here is 2x, and dividing by 2x wouldn't help anything. In fact, it only complicate things. So instead, we can use this rule that it seems to be in this form. We have x squared plus constant squared. So what we're going to do is rewrite this as the integral of dx over x squared times the square root of x squared plus 2 squared. And now we're going to let x equal 2 tangent of theta. That way, if we say dx is equal to 2 secant squared of theta, That way, what we end up having is if x is 2 tangent theta, then the square root of x squared plus 2 squared is going to be equal to 2 secant of theta, because this will become 4 tangent squared theta plus 4. You can factor out a 4 is a 2 squared, so we'll have 2 squared times the secant squared of theta, so it'll be 2 secant theta. Again, this will make it a lot more simple. And you'll notice that also means x squared is 4 tangent squared of theta, which we'll need because we have an x squared up here. So substituting all of that in, we get dx is, I always forget this differential here. We have to we have to put that d theta. So we can rewrite this as dx is integral of 2 secant squared of theta d theta over, now x squared is 4 tangent squared of theta, and this radical right here is 2 secant theta. So we can cancel some things out. This 2 will cancel with this 2. This factor of a secant here will cancel with this factor of a secant. What we're going to end up with is a 4 in the denominator, which, of course, I'm going to pull out in front. We're going to get 1/4 times the integral of secant of theta d theta over tangent squared of theta d there's no d theta down there. Just kidding. So what we can do here is we're going to express everything in terms of sines and cosines and see what simplifies. This is going to be 1/4 times the integral of, this can be 1 over cosine of theta over sine squared of theta over cosine squared of theta. This looks awful, by the way, but let's just extend this bar a little bit so we can realize this fraction is the denominator, this fraction is the numerator, and of course we still have our d theta. All right, ooh, blurry. There we go. So now if we multiply this top fraction by the reciprocal of this bottom one, we'll get 1/4 times the integral of 1 over cosine of theta times cosine squared of theta over sine squared of theta. So this cosine will cancel with a factor of cosine here. We still have a d theta. So we end up getting, this is taking a while to simplify, 1/4 times the integral of cosine over sine squared. Squared of theta, d theta. And guess what? We can keep on simplifying. If we factor out a sine in the denominator, we can get 1/4 times the integral of cosine theta over sine theta times 1 over sine theta d theta. And now this is obviously equal to cotangent of theta, and this is equal to cosecant theta. So we get 1/4 times the integral of cotangent of theta times cosecant of theta d theta. And would you look at that? Integral of cotangent times cosecant is just negative cosecant. So this is going to be equal to negative 1/4 cosecant. I almost started writing out the entire word cosecant there, so it looks messy. Cosecant of theta plus c. But of course, we have to substitute back in something in terms of x. So if we have this triangle, this means if x is 2 tangent of theta, then tangent of theta is x over 2. So it means tangent of some angle theta will be equal to opposite over adjacent, which is x over 2 in this case. And so that means this is going to be equal to the square root of x squared plus 4. Again, this remaining side is always going to be what we substituted out here, because this we determined is equal to 2 secant of theta. So if this is 2 secant of theta, and secant of theta is well, if cosine is adjacent over hypotenuse, then secant will be hypotenuse over adjacent. If 2 secant theta over 2 is secant of theta, which makes sense. So we can make these substitutions. Cosecant of theta, we have negative 1/4. Cosecant of theta is going to be equal to, well, since sine is opposite over hypotenuse, it's going to be hypotenuse over opposite. So it's going to be square root of x squared plus 4 over x plus c, or we can just rewrite this as negative square root of x squared plus 4 over 4x. And there we go. That's how you would solve, never get that plus c. That's how you solve an integral using tangent. We're going to do one more example using the secant substitution, then we'll move on. All right, let's look at one more example of trigonometric substitution. If we have the integral of x squared over the square root of 4x squared minus 9 dx, what can we do here? Well, if you'll recall our identity that tangent squared of theta equals secant squared of theta minus 1, we're going to use that form because we have a function squared minus a constant. So here what we're going to do, this is going to be a little different because we don't just have x squared, we have 4x squared. But here's what we can do. We can say this is going to be equal to the integral of x squared over the square root of 2 squared times x squared, or let's just write this as 2x squared minus 3 squared, and we still have the dx. I want you guys to think about this as this is our x, this is a variable squared, and this is our constant squared. So what we're going to do is let 2x equal 3 secant of theta. That way it'll put it in this nice in this form. So that means that x equals 3 halves secant of theta. So dx equals 3 halves secant of theta tangent of theta d theta. Didn't forget at that time. And that also means that the square root of, well, that also means if we have x is equal to 3 halves times secant of theta, x squared is going to be equal to 9/4 times secant squared of theta. And the square root of 2x quantity squared minus 3 squared is going to be equal to 3 tangent of theta, because that's in this form. We'll end up having 9 times secant squared of theta minus 1. It'll be 9 times tangent squared of theta. It'll be 3 tangent theta. So let's plug all that in. We have x squared is equal to 9/4 secant squared of theta. We have, let's put dx on the numerator. Dx is 3 halves times secant theta of tangent theta d theta. Secant theta tangent theta d theta. All right, that's our numerator. Our denominator is just going to be this radical, which is equal to 3 tangent of theta. All right, that's quite the fraction. But let's see what we can cancel out. Well, right off the bat, we can cancel out a tangent theta here and here. And then we can cancel out 3 here and 3 there. So this entire denominator is gone now. Now what we're going to do is, as usual, pull out these constants to the front of the integral. So we get 9/4 times 1/2 is 9/8 times the integral of secant squared of theta times secant of theta is secant cubed of theta d theta. Now, if you watched my last video where we covered trigonometric integrals, I actually did this integral of secant cubed of theta, and it's equal to, this will be equal to 9/8 times, and the integral of secant cubed of theta is 1/2 times secant theta times tangent theta plus the natural log of the absolute value of secant of theta plus tangent of theta. And now we have our plus c. It's one hell of an integral. So we can multiply these together, we get 9/16. And what's on the inside? Well, we can, as usual, draw a triangle. And if we have this right here, x is equal to 3 halves secant of theta, that means that secant of theta is equal to 2/3 x, or 2x over 3. So if theta, secant of theta is hypotenuse over adjacent, that's going to be 2x over 3. And of course, our third side is going to be this radical right here. And if you did Pythagorean theorem, you'd find that to be true. 4x squared minus 9 under that square root. So here's where we're just going to evaluate all these individual trig expressions and plug everything in. So secant of theta, we already know, is equal to 2/3 x, or 2x over 3. Tangent of theta is equal to opposite over adjacent, which is square root of 4x squared minus 9 over 3, plus the natural log of the absolute value of secant of theta, which is 2x over 3, plus tangent of theta, which again is square root of 4x squared minus 9 over 3, plus c. That is an insane integral. And we're not even done. We still have to simplify everything. So similar to the last problem, this 3 times 3 will cancel out with this 9 in the numerator here. So we'll get that will be gone. This 2 will cancel out with the 16, leaving an 8 in the denominator. And then here, nothing will cancel because we're just multiplying a natural log. So we'll end up getting 1/8 times x square root of 4x squared minus 9, plus, and we still have to distribute this 9/16 to this natural log. 9/16 times the absolute value, times the natural log of the absolute value. And now these have a common denominator, we can just add the numerators. 2x plus square root of 4x squared minus 9 over 3 plus c, and that is our answer. These trigonometric substitution integrals can get pretty wild, but they're nothing compared to what we'll cover next, which is partial fraction decomposition. All right, now the final technique of integration that'll be covered on the AP exam is partial fraction decomposition, which is not actually that hard to do, but the integrals that you end up doing are very long and very time consuming. So we're only going to do a few examples. Even the name is longer than all the other methods. All right, so partial fraction decomposition. Here's what we're going to do. If we have a fraction, and there's one of the names, the fraction, let's say integral of dx over x squared minus 1. We don't have a good way to evaluate this. We could try trig sub because we have an x squared minus 1 here, but we don't have a square root, so things wouldn't work out very well. Well, actually they might, but I don't want to take that risk. Instead, what we're going to do is use this to learn partial fraction decomposition in a simple way. The way we do partial fraction decomposition is first, we have to split up this denominator into all its factors. So this is a difference of squares. It'll factor into x minus 1 times x plus 1. So we're going to rewrite this integral as the sum of two partial fractions. We're going to decompose this fraction into two partial fractions. So the first one is going to have denominator of x minus 1. And what is this numerator going to be? Well, we don't know, but it's going to be a constant. If it was something other than a constant, if it was something with an x or an x squared, this would be an improper fraction. We're not going to have any improper fractions in these partial fractions. So we're going to write some constant a. And then we're going to add the other factor is going to be the denominator now, x plus 1 times b as the numerator, dx. So essentially what we're doing is, here what we'd have to do is find the common denominator, which would be this denominator, and then multiply this by x plus 1, multiply this by x minus 1, add everything together, and we'd have this fraction. What we're going to do is work backwards from that to find out what a and b are. So if you'll notice, if we try to combine the least common denominators, we'd get this is going to be equal to a times x plus 1 plus b times x minus 1 over x squared minus 1. This is all dx. But you'll notice that these two denominators are equal. If we have two equal fractions and the denominators are equal, that means the numerators also have to be equal. This numerator is 1 dx. So that means 1 has to equal a times x plus 1 plus b times x minus 1. And now we can solve for a and b. And the way we're going to do that with the simple case is plugging in the zeros of each of these terms. So first let's plug in 1 to find what a is. If we plug in x equals 1, we get 1 equals a times 2, b is 1 plus 1 is 2, plus b times 0, so this goes away. And we have 1 equals 2a, so a equals 1/2. All right, now b, if we plug in -1 into this equation, we get 1 equals a times 0, because -1 plus 1 is 0, plus b times, now -1 minus 1 is -2. So we get 1 equals -2b, so b equals -1/2. So those are our two constants, a and b. They're 1/2 and -1/2. So now we can look at this integral. I'm going to let this escape here, bring it down here. We have the integral of a is 1/2. Be 1/2. Ooh, I'm going to have to write this bigger. 1/2 over x minus 1 minus 1/2 over x plus 1 dx. So we can factor out a 1/2 from this, and we get 1/2 times the integral of 1 over x minus 1 minus 1 over x plus 1 dx. And now these are two very simple expressions to solve using integration. This is going to be equal to 1/2 times the natural log of the absolute value of x minus 1 minus the natural log of the absolute value of x plus 1 plus c. And we can combine these two logarithms to get 1/2 natural log of the absolute value of x minus 1 over x plus 1 plus c. And that's our answer. Wasn't that bad, was it? Well, it's about to get a whole lot worse because now we're going to be getting into more complex rational functions. All right, now we're going to step up the difficulty real fast. We're going to have the integral of x cubed minus 2x squared plus x minus 4 over x squared minus 3x plus 2 dx. You might say, Ted, whoa, slow down. But this is a common partial fraction decomposition answer that it's going to be the integral. The answer is going to be kind of long, but we're just going to have to deal with it. And I'm sorry to say, for this one, we're going to have to use everyone's favorite polynomial long division. Yeah, I bet you forgot about that from Algebra 2. So since the numerator here is a higher degree than the denominator, we always, when doing partial fraction decomposition, or I'm just going to call it PFD, when we're doing PFD, we always want the numerator to be a lower degree than the denominator. The way we can accomplish that is with polynomial long division, which everybody hates, but it's really not that hard if you just keep track of your negative signs. So it's going to be x cubed minus 2x squared plus x minus 4 divided by x squared minus 3x plus 2. So, in case you don't remember polynomial long division, we're just going to look at the first term of this function. I'm going to say, what do we need to multiply this first term by to get each of these individual terms until we can't anymore? So first we're going to say, what do we need to multiply x squared by to get x cubed? And the answer is going to be x. So we're just going to put an x up here. And we're going to multiply this entire expression by x. And then write it down here. So this is going to be equal to x cubed minus 3x squared plus 2x. And now we're going to subtract this new expression. And to do that, so you don't lose track of your negative signs, I'm just going to put a negative on this, make this a positive, and this can be plus a negative. All right, now these two will cancel. And the only reason we found what we could multiply by x squared to get x cubed is so these terms will cancel and we'll have a simpler expression here. Adding these together, we get x squared, and then adding these together, we get negative x. All right, well, when you simplify, we have to bring down a minus 4 here, and now we're going to say, what can we multiply by x squared to get x squared? And the answer is, of course, 1. All right, now, multiplying this whole thing by 1, I know, real scary, we're going to get that exact expression. And we're going to subtract it, so we're going to put a negative here, make this positive, make this plus a negative. We end up getting 2x minus 6. All right, now, this remainder here, we can't multiply x squared by anything to get this other than 1 over x. We're not going to do that, but what we are going to do is just add this remainder, 2x minus 6, over this this right here, x squared minus 3x plus 2. And now you look, we have a function with a lower degree in the numerator than the denominator. So we can rewrite this. I'm going to write this as two separate integrals now. We have the integral of x plus 1 dx plus the integral of our new function, 2x minus 6 over x squared minus 3x plus 2 dx. All right, now we can do partial fraction decomposition on this. So let's factor out this, this bad boy. So we get x minus 2 times x minus 1. And now we're going to have this can be equal to two fractions, a over x minus 2 plus b over x minus 1. We don't know what these numerators are going to be yet, so let's solve for them. So now we have the numerator is going to be equal to a times, well, when we're simplifying this, when we're combining common denominators, we're going to have to multiply this one by x minus 1. Because in order to get to this denominator, we need to multiply by x minus 1. So this could get multiplied by x minus 1. Therefore, a is also going to get multiplied by x minus 1. Now, if we're going to find this denominator, b over x minus 1 would have to be multiplied by x minus 2 over x minus 2. So this can be b times x minus 2. Again, if you were combining this fraction, this is what the numerator would look like. But this numerator is going to be equal to 2x minus 6, which is the numerator of this. So we get 2x minus 6 is equal to ax minus a plus b. No, we're not going to do that. That's for later. I'm getting ahead of myself again. What we can do, since we have this simple case, is we can just plug in these zeros. So let's plug in 2 first so we can find a. So we get 2 times 2 minus 6 equals a times 1 plus b times 0. That's gone. We have 4 minus 6 is negative 2 equals a. So yeah, a equals negative 2. And now, if we plug in 1 so that a goes away, we get 2 minus 6 equals 0 plus b times 1 minus 2 is equal to negative b. That means negative b is negative 4, so b equals 4. Alrighty, now, here's what we're going to do. We're going to now put these numbers in this function. So we get the integral of a is negative 2 over x minus 2 plus 4 over x minus 1. You can even check with yourself to make sure if you combine these fractions, you'd end up getting this one here. This would be negative 2 times x minus 1, which is negative 2x plus 2 plus 4x minus 8. So that'll end up being negative 2x plus 4x, which is 2x, plus 4 minus 8, which is not correct. Minus 2, plus 2 minus 8, which is negative 6. There we go. I faked myself out. So yeah, these two fractions are correct. And now these are both very simple to integrate. But notice we can't forget this guy right here. We still have added this little integral of x plus 1 dx, saying, don't forget about me. All right, so this integral is going to evaluate, of course, to 1/2 x squared plus x. This is going to be minus 2 natural log of the absolute value of x minus 2 plus 4 times the natural log of the absolute value of x minus 1 plus c. And then, of course, we can combine these two. So we get 1/2 x squared plus x. And you know what? If we combine these two, we'd have to move this 2 and this 4 up into the numerator. So I don't really think we should do that. I'm just going to rearrange this as 4 natural log of the absolute value of x minus 1 minus 2 times the natural log of the absolute value of x minus 2. Because to combine two logarithms, they have to have the same coefficient in front of them, and I don't want to do that. So we're just going to leave it like this, and this is a perfectly acceptable answer. Now you can see this is getting a lot more complicated. And you just wait, because our last problem is going to be the most complex yet. Okay, so far with partial fractions, we just looked at when there are linear factors in the denominator. But what about when there are different degrees of factors? Let's look at some examples. We have the integral of x cubed minus 4 over x plus 1 squared times x squared plus 4 dx. Now, this is a way more interesting function because first of all, we cannot simplify this. Second of all, we have a linear factor repeated here. So this is going to be equal to a more complicated PFD. It's going to be equal to a over x plus 1, because there might just be a factor of x plus 1, plus b over, oh, my pencil lid broke, b over x plus 1 squared, because there might be a standalone factor of that. Plus, now, for this one, in order to get it, have the same degree in the numerator and the denominator, we actually have to write this as cx plus d over x squared plus 4, because there's degree 2 in here, we have to go 1 degree lower in the numerator. But that means that since this is a linear factor repeated, we're going to go a degree lower. We're not going to, technically, if you factor this out, you get x squared plus 2x plus 1, and that's a quadratic, so you'd say, why isn't this bx plus c? But it's just a linear repeated factor, so it's just going to be b. And this is dx. Now, as you can imagine, solving this is going to be much, much more involved than solving the other two. So we have our numerator, x cubed minus 4 is going to be equal to. Now, if we were combining these all into one, what will we need to multiply this denominator by in order to get this denominator? Well, we still need another factor of x plus 1, and we still need to multiply by x squared plus 4. So this is going to be a times x plus 1 times x squared plus 4. Then b already has two factors of x plus 1, so we'd only need to multiply by x squared plus 4. And then cx plus d, this fraction we already has a factor of x squared plus 4 in the denominator, so all we need to do is multiply by x plus 1 squared. Now, finding the zeros of this is not going to be the same. We're not actually going to plug in the zeros of this. Finding the solutions of this will not be the same. We're not going to plug in the zeros. If you plug in -1 here, this will go to 0 and this will go to 0, which would work. But if you plugged in, you can't really plug in here anything here except 2i or -2i to make this go to 0, and that would make these two go to 0, and then we still have two variables. But so anyway, if we have multiple things like this, doing the simple method is not going to work. What we're going to do instead is FOIL all of this out, or FOIL and just multiply, distribute everything out here. So I already did that for you, so I'll just write it down without making you guys watch me go through the struggles of doing that. For x cubed minus 4 is equal to ax cubed plus ax squared plus 4ax plus 4a plus bx squared plus 4b plus cx cubed plus 2cx squared plus cx plus dx squared plus 2d plus d. That is a very long numerator. Now what we're going to do is combine a lot of the coefficients into based on what their degree is. So we have x cubed minus 4. Let's see, what are coefficients in front of x cubed? So we have ax cubed plus cx cubed. A plus c times x cubed if we use distributive property. What's our x squared going to be? We're going to have ax squared plus bx squared plus 2c x squared, no x squared in here, plus d times x squared. Now our linear term is going to be 4ax plus, there's no x's here, cx, so we have plus c plus, there's no, this should be a dx plus d, so we have plus 2d times x, and then our constant term is going to be 4a plus 4b plus d. All right, now what can we do with this? Well, since we have x cubed is going to be equal to x cubed plus something equals a plus c x cubed plus something, no matter what all this is, this x cubed is going to be the same as this x cubed. That means the coefficient 1 is going to be equal to this coefficient, a plus c. So we have a plus c equal to 1. Now, there's no quadratic term, and there's no linear term. So our quadratic coefficient here, a plus b plus 2c plus d, it's got to be equal to 0, because that would make this 0x squared, and sure enough, there's no x squared here. Likewise, our linear term, since there's no linear here, is going to be 4a plus c plus 2d, that coefficient is equal to 0. And finally, our constant is -4, which means our constant here is 4a plus 4b plus d, equal to -4. This is a very complicated system of equations to solve, so you can just plug it into your calculator. If you have a graphing calculator, you can go to the apps, go to Polysmult2 or whatever that stands for, and then go to simultaneous equation solver, plug all this in, and you'll get that a is 1/5, b is -1, c is 4/5, and d is -4/5. So those are our coefficients. And now let's rewrite this integral with those new coefficients. So we have the integral of, it's going to be a doozy. A is 1/5 over x plus 1 plus b is -1, so we're going to minus 1 over x plus 1 squared plus, now cx plus d is going to be 4/5 x minus 4/5. So we have 4/5 x minus 4/5 over x squared plus 4. All of that dx. All right, so what we're going to do now is split these up into separate integrals. So first we're going to have, and again I'm going to move the constants out to the front. You know how I am. We have 1/5 times the integral of 1 over x plus 1, or dx over x plus 1, minus 1 times, we don't need to write that one, minus the integral of dx over x plus 1 squared. And what I actually can do here is this numerator, we could split it up into 4/5 x over x squared plus 4 minus 4/5 over x squared plus 4. So I'm going to write those each as a new integral. So we're going to have plus 4/5 times the integral of x over x squared plus 4 dx minus 4/5 times the integral of 1 over x squared plus 4 dx. All right, we can evaluate each of these. So this is a simple logarithmic one. We get 1/5 times the natural log of the absolute value of x plus 1 if you did simple U-sub. This, if you did, again, simple U-sub, it's power rule, so this would be minus, it'll be minus a negative, so plus 1 over x plus 1. This is really x plus 1 to the negative 2, so using power rule, that would be negative 1 times 1 over x plus 1, and the negative 1 times this negative 1 would cancel out. Now, this one, we'd have to use U-substitution. We'd let u equal x squared plus 4. du would be 2x. That would cancel out with this x, and we'd end up having a factor of 1/2. So we'd have 1/2 times 4/5, which is 2/5, times the integral of, times the natural log of the absolute value of x squared plus 4. If you're confused about that, you can about these three, you can go look at my video about U-sub. I'm taking shortcuts here, which I hope by this point you're more comfortable with U-sub, so you can just look at it and do the substitution. And then finally this one. This one we're going to have to go back a little bit to trig sub and figure out a very important identity when doing partial fraction decomposition. If we have, let's go over here, the integral of 1 over x squared plus a squared dx. There's no square root here, but we're still going to use trig sub, and let's see what happens. We're going to let, this looks like tangent, so we're going to let x equal a tangent of theta. So that means dx equals a times secant squared of theta, d theta. And that means x squared plus a squared will equal a squared times tangent squared of theta plus 1, which is equal to a squared secant squared of theta. So, plugging all this in, we'll get the integral of dx is a secant squared of theta, d theta, and this denominator is equal to a squared secant squared of theta, and this will cancel, this will cancel, this will cancel with a factor of a here. All we'll get left with is d theta over a, which is a constant. So since we just have a constant here, the integral will be equal to theta over a plus c. But now we have to figure out what theta is in terms of x. So here, if x is a tangent of theta, that means theta is equal to, theta is equal to the inverse tangent of x over a. So plugging that in, we get this integral is equal to 1 over a, using this, times the tangent of inverse of theta, which, theta is equal to tangent inverse of x over a. So all that, which I'm going to put in a box over here, was used to establish this fact, that integral of 1 over x squared plus a squared is equal to 1 over a times tangent inverse of x over a plus c. So I'm sure you can see why we need that here. Here a is 2, so this is going to be equal to 4/5 times 1 over a. 1 over a will be 1 over 2, so only 4/5 times 1/2, which is 2/5 times the tangent inverse of x over a, which is going to be x over 2 plus c. And that is our answer. Now you can see why these partial fractions get very, very complicated, even though the technique isn't that hard. So just to review, the key idea here is to work backwards like you would to find the least common denominator. We know the least common denominator you split it up into all the individual fractions, figure out what the coefficients are, and take each integral of that individually. So those are the other techniques of integration. I hope that it'll help you for the AP exam. Over the weekend, I'm going to do a couple videos on two important types of FRQs. So stay tuned for that. See you next time.